Okay, let's get going. Put the answer key for the homework up on Canvas. So let's go over that first. Large, it's bigger. Okay, so the first question is about expectations in bowling, and what you needed to do in order to answer this is to break up the total expectation for the 10th pin, 10th roll, 10th frame of bowling into 3 or 4 different scenarios, get the conditional expectation within each of those scenarios, multiply them by the probability that this scenario comes into play, and then add it all up. So you're given a whole bunch of stuff. You need to probably create the joint probability table like we did in lecture. You can just copy the code for that. And there's a few things that are evident or calculatable from this table. One is the probability of a strike, which is just 10 and 0. Another is the probability of a spare, which is the sum of all those on the anti-diagonal. And finally, the row sums are the marginal probability of knocking down some number of pins when 10 are upright. And then as a preliminary calculation, we can get the marginal expectation of 1 roll and the expectation of the sum of 2 rolls, starting with 10 pins. And so like I was saying, you can write the total expectation as a weighted sum of conditional expectations. What happens if you get a strike on the first roll? What happens if you don't get a strike, but you do get a spare? What happens if you don't even get a spare? So in the case of a strike on the first roll, you get 2 more rolls. And so the conditional expectation is going to be 10 from knocking down all of them on your first roll. And then you get 2 more rolls. And so you can add on the expectation of 2 more rolls there. But the one difference is that unlike or all the previous frames, 1 through 9, we had a spot in that 2-dimensional table for, if you do 10 and then you sort of automatically get 0 on the next one, the second roll doesn't even happen. But on the 10th frame, if you get 10 following a strike on the first roll, you also get 10 on your second roll. You get a third roll with all 10 pins up, and so you need to add on the expectation for a roll with 10 pins multiplied by the probability that you get a strike on your second roll. Add all that together, multiplied by the probability of getting a strike on your first roll, and you've taken care of the top line there. Second line is actually probably the easiest one. Want to multiply the probability of getting a spare times 10, which is what you get for your first 2 rolls, plus the expectation of your third roll when there's 10 pins up. Finally, the third line there, what's the conditional expectation when you do not even get a spare? And so there is no third roll to give you extra points or whatever. You can go through the math on that. It amounts to the expectation for 2 rolls minus 10 for times the probability of getting a strike or a spare. So neither of those occurred. So you have to subtract away 10 from the usual expectation for what happens on 2 rolls. So you add all those things up, should get 16.8. It says to do that with math rather than simulation, but you can always check your work with a simulation many times for the 10th frame of bowling, and then just take the mean of those. Also comes out to 16.8. Okay, so if you have questions, you can look more slowly through the answer key, which is on Canvas. Second question refers to probability in this particular hand of poker that occurred a couple years ago. And as we see on the last question, it's sometimes a bit, or a lot of times actually, a bit difficult to come up with good examples where the frequentist view of probability makes sense. You really are doing, the same process, independent times, over and over and over again, and you're worried about the long run properties of all those estimations. It's pretty easy to come up with, the Super Bowl or something like that, where it clearly makes sense to take the subjective view of probability, or the Bayesian view. Poker is the only example that I can think of that really combines the objective and the subjective view of probability simultaneously, because sort of the shuffle machine ensures that there's a uniform probability of each card being turned over, and what cards you can see, so you know what cards are left in the deck that you can't see. But that's really only half of what's going on. That would be sort of enough to think about blackjack or something like that. But in the case of poker, the other half of it is conditioning on the information that comes from the other people betting, conditional on the body language of the other people, etc. And that aspect of it that has to do pretty clearly with the subjective view of probability, updating as you get additional information that comes from the bets, etc., is really what makes poker a more interesting game than blackjack or Go Fish or whatever other things like that. And so you can kind of see that going on, particularly in this hand. So what's the probability of getting dealt 2 aces? Well, that's equal to the marginal probability of being dealt 1 ace. There's 4 of those in the deck of 52 card deck, multiplied by the conditional probability of being dealt a second ace, given that you've been dealt a first ace. And so that would be the conditional probability 3 over 51. There's 3 aces left in the deck, 51 cards. And so that comes out to about 1 in 221 hands, or you could do the decimal approximation of that. And then what is the probability of being dealt any pair, not just the ace? Well, it's going to be the same for each of the 13 different value cards in the deck. So it's 13 over 221, which I wrote twice, but it's only true once. You can do a simulation to check your work on that just by making a sample space, which is the deck of 52 cards, drawing 2 without replacement. And so that is what leads to conditional probability, and you get stuff that very closely approximates the analytical calculations. So like I was alluding to at the beginning, poker is really about conditioning on the information that comes from the other people's bets. And if you have to go first, then there's no information available from the other people's bets yet. And so you can only condition on the information that you have in your hand. And that's not nothing. But the people who go after you can condition on, whether you bet, how much you bet, whether you fold, etc. And so they have more information to update their beliefs about what you have than what information you had about their hands when you had to bet. And so if you're in a bad situation, you can fold. If you're likely to be in a good situation, you can bet. And that is going to, result in sort of systematically worse outcomes for the people who have to go first. And that's why they rotate. This ties into the idea of decision theory. So, since all that is true, you're usually not going to be getting positive results when you have to go first, unless you have a really good hand, like best 10%, best 15%, etc. And what the idea of expected utility theory or decision theory that we talked about one of those weeks is, basically how you can interpret this is if you have the hand that's at like exactly 15%, the best one, then your expected value for a hand like that is going to be about 0. If you have, top 10%, something like that, your expected value from that hand, if you bet, is going to win. If you're like, bottom 80%, something like that, the expected value if you bet on that hand is going to be negative, and you should fold. Clearly, pair of aces is the best hand that you can be dealt, and so you're always going to be betting that, and then it folds around to Connor Drinan, who also has aces, and this was an extraordinarily unlikely event to go. In order to calculate the probability of that, you have to do sort of the multiplication rule 3 times rather than just once every time an ace is given to somebody. That's 1 fewer aces left. And so you just do the fractions. It comes out to about 1 in 270,000 deals if there were only 2 players being dealt. In this case, there's 6 players at the table. They all get 2 cards. And so the probability that any of 2 of them are both dealt a pair of aces is going to be 6 choose 2 divided by 270,000 whatever. And so that bumps up the probability to a still very small number. So this was an unlikely situation to happen, as sort of reflected in the expressions of the players when they saw that that had occurred. Bluffing goes back to this idea of expected utility and conditioning on the information that comes as the bets come in. And basically the idea of bluffing is to bet the same amounts that you would have even though you have a not such a great hand, but to bet the same amount as if you had a good hand or a better hand than what your opponent is likely to have. And that at least raises the doubt that you have a better hand than your opponent, when in fact that is not true, or it changes the expected utility calculation as to whether the opponent should bet or should fold. And in some situations, you can get positive expected value from bluffing. This is probably not one of them, just because the person who goes first has such a limited range. It is unlikely to be folding, from any bet that comes behind them. And in fact, he didn't. Both of them raise it up until they're both all in. Let me see what happens. One of the guys, Terry Katz, in the baseball cap says, well, even before dealing the remaining cards, can we just chop this? How can we make sense of this from a Bayesian perspective? And in order to do that, you need to calculate the expectation and the variance or a standard deviation of the results. Looks like every math thing I did came out twice somehow. We'll get that fixed, but hopefully at least one of them are correct. So the expected number of chips gained, you just multiply the probability of their occurrence by the value, conditioning, everything that's in the pot is already a sunk cost. So there's a 0.96 chance that they each get half the pot, a 0.02 chance that either one of them gets the whole pot by making a flush, and a 0.02 chance that each of them gets 0 when the opponent makes a flush, and that all cancels out to 5,250,000 in chips. Apply the same idea, but now to the function, x minus its expectation squared, and the squaring process of it results in a variance that's 0.04 times 5.25 million chips. So the standard deviation is going to be the square root of that, which is like 20% of the expectation. And the reason why, he's saying something like that, it's one thing to bet like $10, in which case it's sort of reasonable to say that people would be risk neutral about something like that. But when you're talking about millions, then it's unreasonable to assume the person is risk neutral or risk seeking. And so if they'd had the option, their utility would be greater if they just received their expectation and moved on to the next hand, or even if they just received a little bit less than their expectation, if they could just go on to the next hand and not take the realization of what happens on the next 5 cards. Of course, there's a translation between poker chips, which are not that useful, and money, which is. But in this case, there was a $15 million prize for first, and there was about 18 players left, and both these two people had kind of above average number of chips when the hand started. So really the expected value of each chip was about $1. So it's actually pretty close that they were, you know, basically having a very high variance lottery on, you know, $500,000 worth. At one point, Drynan leans over to Scott Seaver and says, you know, I thought cats had to have a pair of kings. And here you sort of have to get into his mind a little bit, but basically it'd be reasonable to assume that cats would not have, you know, raised so much. He would not have talked the way he did if he had anything other than some aces and some kings. But Drynan had two of the aces, which drastically limits the number of hands cats could have with an ace in it. And so the probability that he has two kings, given that he only has aces or kings, comes out to 2/5, which might seem a little bit low since Connor Drynan said, you know, I thought he has to have kings. And so, you know, you didn't have to work it out. But maybe what he really meant is that he didn't think that, you know, cats would act that way unless he had, you know, aces or kings or the ace and king of the same suit. So he wouldn't have done that. He would have just called if he'd had ace and king of different suits. And so that further reduces the number of hands that he could have and makes the probability of kings still up to only 2/3, which is sort of far from certain, but, you know, he would have behaved or, you know, both of them would have gone all in basically, you know, with any of those. So then flop comes, 2 hearts in the middle. Need to calculate the probability that one of them gets, or cats at this point gets a flush in hearts. And so you can go through the remaining cards in the deck. This is slightly tricky because one of the players that folded had the 6 of hearts in his hand, but Katz didn't really know this when he said, you know, I have a 4% chance of winning. But basically it comes down to there's like 10 hearts that are unaccounted for, 45 total cards that are unaccounted for, and we need the joint probability that the next 2 are hearts. And so that comes out to 1/22. And that's like 4.5%. So really between 4 5. One of the other players at the table, when it, you know, comes down to the last card, says, I feel like it might, you know, be a flush. Is this a Bayesian statement? And so there's a way to interpret that it is, but it's not a particularly reasonable interpretation. So technically from the Bayesian point of view, you can come in with any set of beliefs. Like this deck could be like not a real deck. It might only have 4 hearts in it, in which case it would be like impossible that the last card would be a heart, even though you're updating your beliefs, you know, as you see more and more cards. But a professional poker player knows that there's exactly 13 hearts in a deck, in which case, you know, like Scott Seaver says, it might be a heart that comes off last. So in order to interpret this statement as not just being tautology, then it has to be sort of, you know, you have this like premonition or something like that, something beyond what's implied by Bayes' rule, that it could be a flush. Independence. So a number of ways to think through this, but basically the bottom line it comes down to, if you're dealt 2 aces, those have to be from different suits. And that eliminates the possibility that you could get a flush by having 2 of the same suit and then 3 out of the 5 from the middle being that same suit. So the only way that you can get a flush when you have two aces is if 4 of the 5 are the same suit and that matches with one of the suits that you have, or all 5 in the middle are of the same suit. But the fact that getting two aces rules out the first possibility that you can make a flush with 3 out of the 5 means those two events are not independent. Salif, did you have a question?
Yeah, basically the point before, I wasn't entirely sure, like, so like what the result was now. Is it the psychology? Is it both as possible, depending on the perspective you take?
Yes. So in theory, it is possible that you could believe absurd things about the deck coming in, but professional poker players don't. They would have already lost their money a long time ago if they didn't believe that there's 13 of everything 4 suits in the deck. And so in that sense, it's just like a tautology. And so why would he even say it unless he was attempting to say that, like, he has this feeling in his gut that
Like I just run it in a way like it is likely, so to say, that the next card is a heart. For me, the likelihood is like decreasing every heart that is like being built. And that sense it's not Bayesian statement, but it's not like objectively updating based on what happened before.
Yeah. So with every heart that turns up, the probability that another heart is going to come up next is lower because you've taken it out of the deck. However, with every heart that is turned up, the probability of getting a flush is higher because you're already one more step there. And so that, all follows mechanically from conditional probability. That's just like obvious.
But that's not what I'm saying. I feel like the next.
Yeah, it's like my horoscope says, Anyway, so okay, we got that. There's some speculation that this might be sort of the most extreme hand in the history of poker. I don't know that is really true, but I think the reason why it made for such good television is, when you're dealt aces, you have a really good feeling about how this hand is going to go, and when you see the other person have aces, then there's a really strong probability that you're going to split it and just go on to the next hand. And then to lose all your money in that situation is a really unlikely outcome. This is going to be hard to read with all the duplicated HTML, but basically we already found the probability of 2 people getting aces. That's like 6 choose 2 divided by 270,000, and then you work out the probability that 4 out of the 5 cards, exactly 4 out of 5, or 5 out of 5 cards in the middle come out to be the same suit. That's another very unlikely thing. Multiply that marginal probability by a conditional probability, and you get something on the order of, this is 1 in 2.4 million hands sort of event, and it got played for an extraordinarily large amount of money. Bernoulli-Poisson question: several ways you could go about doing this, but basically have to do marginalization. So you could just do a lot of simulations from Poisson and see how many times they sum up to 4. You could explicitly do the marginalization aspect of it, in principle summing from 0 to infinity, but actually, if you only have like 3 Bernoullis, there's no way that can sum up to 4. So you could start this at 4. You don't really have to go up to infinity because the numbers get very small quickly. It would suffice to just run it up to 100, sum that joint probability over n, you get something like 0.07. In principle, you could do some math that shows the marginal distribution is actually also going to be Poisson with expectation 2/3 times the square root of 7. 2/3 comes from the pi, square root of 7 comes from the mu. You obviously did not have to do that, but you would get out the same answer there. So that's just the mechanics of marginalization. Last question about the frequentist approach, try to come up with an example where the frequentist perspective on probability seems to make sense. Something when you actually have some sort of a random sampling mechanism, is some sort of random sampling mechanism that is going to occur, multiple times or a lot of times, really, and then you're interested in the behavior of the estimator over all of the times in which this is conducted. And so probably the easiest places to think about these sort of things are official statistics of governments, like the unemployment rate, and you say, okay, we're going to calculate this thing. We could calculate a confidence interval in 19 out of 20 months. We would expect the confidence interval to contain the true unemployment rate, but we don't know which out of the 1 out of the 20 doesn't. And so, that's a decent example. But at the same time, not that you had to, but there's ways in which you could question this. So for the people that the unemployment rate is important, they're making decisions about that. They're projecting what it's going to be in the future, and they're doing something that seems, pretty Bayesian, not based on, what's the long run coverage of the confidence interval estimator of the unemployment rate. So people like Federal Reserve chairs, more see this as updating their beliefs. And Alan Greenspan gave a speech that, basically said this is how he viewed his job, and a bunch of other central bankers wrote commentary on it. You can see a link to that. But anyway, as it happens, the unemployment rate for the United States is going to be released at 8:30 tomorrow on the internet. And unless, Trump tweets something, the newspapers will be, talking about the unemployment rate all morning. So you might listen to see if, anyone who's like blathering on about what the estimated unemployment rate is, doing so from a frequentist perspective, or are they sort of receiving that information and then immediately going Bayesian on it for whatever purpose? Yes.
But there's sort of survey. There's sort of two. One is like you're averaging over time, which I think is like double. But then there's also saying that however number of people you survey is representative of any sample for that day or that month. That seems to be much more frequentist, right? So if I sampled 100 people in a county, that's the unemployment rate in a county. That's a much more frequentist duration, go from that estimate to a sentence.
I would say the second thing you're talking about is more about, good survey design versus bad survey design. And you would, even if you're going to apply Bayesian analysis, you want to have good surveys, have it be representative of the population, stuff like that. So, and I think, particularly with government statistics, there's sort of the perspective of the data collector and what their sort of objectives are in doing this. Same thing with the census when they release like 5% of it. And then there's the question of, well, the person who's like downloading the data, what did they use it for? And are they using it for something that's like basically frequentist or basically Bayesian? Regardless of whether they sort of internalize that debate. Questions? Okay. So, just a bit about that before we go on. Not a number, but like a small number of people emailed me, over the last week or whatever, and it's like, yeah, I don't really understand how to do any of the problems on the homework, so I have to drop the class. And that's kind of frustrating when I didn't realize you were in the class to begin with, because over the first 3 weeks, you didn't ask any questions about the stuff that, subsequently appeared on the homework. And so there wasn't really much of an opportunity to give you some hints or sort of point you on the right track, or otherwise get a better sense of how you're doing. So, I mean, it's good to ask questions because it, clears up misconceptions and things like that you might have. It simultaneously can help other people in the class that are sort of struggling with the same question but may not be able to articulate the question in exactly that sense. But it helps me sort of understanding where the distribution of, you know, understanding versus, you know, confusion is in the class at a particular point in time. And it makes it easier for me to like prepare the material and the homeworks and stuff like that. So there's a lot of people still haven't really, you know, put anything up on Piazza or anything like that, and you're sort of a black hole in terms of this. So keep the questions, keep the discussions going, whether it's about the answer key or the stuff in the lectures, stuff that you read, you know, links to blog posts that I, you know, put up, all kinds of things like that. All right. So flipping over to the stuff for today. We actually are going to get into a little bit of Stan. So this is actually kind of relevant for the first time, but Columbia developed Stan. I use Stan business purposes. That creates the appearance of a conflict of interest to think about in these presentations. And one of the companies that I have worked with a little bit is Novartis, the mostly Swiss, but really they're a multinational company that develops drugs. And so the situation that I want you to think about yourself today is actually not a Novartis drug, but this small biotech startup called MAP Biopharmaceutical has for the past several years been developing a drug that they claim can cure someone who has Ebola. So it's not a vaccine injection that you take after you get Ebola, and they claim it's still in development, but they claim that it can cure you. And so the question I want you to think about is that if you were the Surgeon General or whatever, would you approve MAP Biopharmaceuticals Ebola drug for, you know, use people who have Ebola? So that is sort of a very classic decision theory problem, and it gets to the issue of not so much with this, but how does the FDA make drug approval decisions? In point of fact, they allow companies to do Bayesian stuff for the first 2 phases, and then the 3rd phase, where it ultimately gets decided, they make them do frequentist stuff, and that's been controversial. There's a lot of Bayesians and a lot of frequentists in the FDA and in the corresponding like European regulatory bodies. So this is actually an active question, albeit not a totally social science one, but it's still something that's pretty easy for a lot of you to think about, and to think about developing priors for a situation like this. And it leads to a game that I like to play called The Prior is Right. Do I have music? So where are my mailman School of Public Health students at? Come on down. You are the next contestant on The Prior is Right.
What?
And you all have to yell out arbitrary numbers to either help them or confuse them, however it goes. Taylor?
I'm just a nurse, so.
That's close enough. All right, so the symbol. All right. So, Sebastian.
Yes.
What is your prior mode for the probability that someone who has Ebola takes the drug would survive?
0.
0 is a better answer than 7, but I like it. So you think it's absolutely impossible that there could be a drug that cures Ebola?
Fine. 0.2.
0.2! Next we have Tori. Yes. Tori, what do you believe is your prior median for the probability that this drug would cure someone with Ebola? Must be between 0.2, which is what Sebastian said, and 0.5. So the sort of over-under point. There's an even chance that it's less than this, even chance that it's greater than that. 0.35. Okay. So Taylor, suppose that I told you that in clinical trials with 21 subjects who had Ebola, 21 out of 21 were cured. What would you now say is your prior mode for the probability that this would cure someone who has like Ebola from the wild as opposed to like clinical setting? Closer to the 0.35. Anyone want to jump in with a updated prior median between 0.35 and 0.5? Knowing that 21 out of 21 subjects were cured?
That's a clarifying question.
Clarifying question.
What does cured mean?
Like.
How does that help?
For you. Oh man, I thought you
They
were support me.
no longer exhibited the symptom.
Well,
I don't know.
Because one thing, like they found Ebola in people's eyes after they like survived and
Yeah, so like the symptom, they can like go back in this. Their symptoms are gone.
Okay.
Yeah. So do you have an updated prior median?
No, I didn't know.
Tori. Thinking. So the over-under on the cure probability increases. What are you talking about?
What's the survival rate of people normally
With or without treatment?
without treatment?
It's between 30 and 70%.
Depends on the strain.
Okay.
So let's just call it 0.4. All right. So Taylor, suppose that I were to tell you that out of the 21 subjects who survived after taking MAP biopharmaceuticals drug, 21 out of 21 were monkeys. What would you now say is your prior mode for the probability that this would cure a person with Ebola?
What type of monkeys?
I'm a political scientist. I don't know. The monkeys that are supposed to have very similar immune systems to people.
You come closer to the 0.3.
Back to 0.3.
To the 0.4 probably. I don't know.
So you're going
A
up.
little less than what I would before
Okay.
in the prior situation.
That's a little weird because you didn't know they were monkeys. I mean, certainly the fact that they're monkeys introduces more uncertainty as to how well it will work in a. Prior median between 0.4 and 0.5?
I'm still down. I'm not between 0.4.
You're less. Okay. Well, Bayesians can come in believing anything you want. Okay, finally, Tori, suppose that I were to tell you of the 21 monkeys who were cured by this drug, all 21 of them were injected with the cure 1 hour after they were injected with the Ebola disease. And in subsequent trials with 21 monkeys who were injected with the cure 3 days after being injected with the disease, 14 out of 21 monkeys survived to the end of the study. Then they got whacked because can't have monkeys with Ebola. Might escape roaming around.
See, because they're not cute. I mean,
They still have the virus
It's important to stay
in them, but they survive for like months, you know, after getting the drug. So prior median or prior mode, whichever you'd like, for the probability that it would cure a person who presumably, you know, there's going to be a bit of a delay between when they're exposed and when they, you know, start getting treatment.
Okay, so my thought process is that its true efficacy in the monkeys is, let's say, 2/3, 67%, something like that. And then it's probably, we don't know if it's more or less effective in humans. But given that it's, you know, we want to be conservative, given that we're giving this to humans, I would say that my prior is slightly higher than the original, but nowhere near like 1.
That's really the process that you have to go through when thinking about something like this. What previous information you have, even if it's not like perfectly relevant to the situation that you're facing, helps you think about, you know, the probability distribution for these or that things. Robert.
How do you limit the probability to 0.5?
You'll see in a second. It makes the math coherent. Anyway, so that was very good. Hand for all our members to our project. Everybody is a winner. No, it's a prize. All right. So, in point of fact, what I was really asking about, and this goes to what I was telling with Robert, we're thinking about our prior for the cure probability, which is going to be some number between 0 and 1 in terms of a beta distribution. Beta distribution has 2 shape parameters, A and B, that must be positive. But its CDF is essentially impossible to write down in a useful form, and that can make it a little bit hard to think about what would reasonable values of A and B mean. But you can, if you have 2 shape parameters, A and B, and you have 2 pieces of information, the mode and the median, then you can solve for the values of A and B that are consistent with your beliefs. And so the mode, capital N, is given by this expression, but there's only a mode if A and B are greater than 1. If they're less than 1, then the beta distribution is like U-shaped like this. Consequently, it does not have a unique mode. In order for it to have a unique mode, the median has to be between 0.5 and the mode. The median doesn't have an exact expression, but in the conditions where the mode exists, you can approximate it very well by this one. And so if you have 2 equations and 2 unknowns, A and B, and 2 knowns, the prior mode and the prior median, you can solve those for the unknown thing. And I gave a link where you can actually, if you don't trust yourself to solve 2 equations and 2 unknowns, do it on Wolfram alpha, which is totally fine. And it also tells you the condition that the median has to be between 1/2 and the mode. The expectation of a beta distribution is A divided by A plus B, and that has to be closer to the median than the mode. But if you ask someone what's the, you know, expected value of the cure probability, technically you're asking them to do an integral in their head, and that's probably not going to go so well. So I prefer, when asking myself or other people about their prior beliefs, when possible, to use the mode or the median rather than the mean. That way they only have to think about like 1 point rather than doing this internal integral. But definitely ask about measures of central location rather than like variance or skewness or something like that, that people are even less likely to be able to wrap their heads around. All right, so we had some prior modes, some prior medians there. We could solve for the corresponding values of A or B that corresponds to what any public health professional might believe about this probability that this could cure a person. So getting into Stan a little bit, this could all be done in R, but we're going to start to learn about Stan. So this is a function that I wrote in the Stan language to draw from the prior predictive distribution if N people with Ebola take the drug, how many of them Y survive. And so if you write a function in the Stan language, it needs to be enclosed in a block called functions with curly braces around it. Main difference between Stan code and R code, Stan code is going to be translated into C++ and compiled. Therefore, the first time you mention something, you have to say what type of thing it is in order for the computer to allocate enough memory for it. So I have a function called Ebola RNG. This is going to generate random numbers, and so it has to have a RNG suffix in order for Stan to recognize that. It's going to return a vector of draws from the prior predictive distribution. In particular, it's going to return S draws. So I need to pass the integer S as one of the arguments to the function. I have real numbers, capital M and lowercase m, corresponding to the prior mode, prior median, respectively, and values for the data, N people with Ebola, Y, the number of survivors. Those are both going to be integers. And so if I go back to the previous page, I have these expressions mapping from the prior mode and the prior median to A and B, which are going to be real numbers. And so when I specify those for the first time, I need to indicate that they are real numbers. Once you have defined something, you can use it in subsequent statements. So I calculate the denominator just once and use it twice because it's the same for A and B. Then I'm going to allocate a vector of size S called out. This is the thing that is going to be returned by the function. I initialize of integer lower s to 1, and then I start a while loop as long as little s is less than or equal to big S. And this is where I draw from the prior predictive distribution. So I'm going to take a real draw, which I'll call pi tilde, from the beta distribution random number generator with parameters A and B. So this is a draw from my prior distribution. I'm going to use that to draw an integer y tilde from a binomial distribution with size n and success probability, the realization that just came from that beta random number generator, pi tilde. Then I'll use an if clause to check whether my realization of y tilde, the simulated number of survivors, is exactly equal to y, which I pass in the actual number of survivors. If that is true, I keep my realization of pi and I stick it in my holder, which is going to go out, and I make s 1 bigger. If not, then I just throw away that draw of pi tilde and keep on while looping. Eventually, I'm going to fill up my vector to go out, and then I return it. First, in order to make this easier to plot, I'm going to sort it from biggest to smallest. So what I've done here is drawn from the prior predictive distribution to draw from the joint distribution of pi, the success probability or the cure probability, and y, the number of survivors. And when that realization of y tilde matches the data that I have on y, I know my draw of pi was good, so I'll keep it. If not, it doesn't satisfy the condition of my data, then I'm going to throw it back. So it's just like fishing. And now you get updated draws from the distribution of the cure probability pi, which you can then easily plot. So in order to do this, you need to load the rstan package. It has a function called expose stan functions. If you save the previous slide, or it's on Canvas now, is ebola_rng.stan. It will compile those functions and export them to R for you. So now I just put in like maybe reasonable values for the mode and the median in R. I translate them into A and B in order to use later. In point of fact, there were 7 doctors and nurses who were exposed to Ebola in the last outbreak in like 2014. They flew them to the CDC in Atlanta, and they gave them MAP Biopharmaceuticals drug, which had not yet been approved for like general usage. But since they already had these 7 people who'd been exposed to Ebola in Africa, they gave them the drug. And of those 7 people, 5 survived and 2 died. So we want to update our beliefs about how successful this drug is. So expose stan functions will give you a function in R called Ebola RNG. You call it with the specified arguments. You get back 10,000 draws from the posterior distribution of pi, which you can then plot the CDF of in black here and compare it to the prior CDF for a beta distribution with shape parameters A and B. So before you updated your beliefs. And you can see after observing 5 people who are cured out of 7 who were exposed, that causes the posterior distribution of your beliefs about the cure probability to shift over to higher numbers to get more concentrated. So it has a steeper slope around here. And basically eliminating the prospect that the cure probability is actually less than 0.2, given what you already knew about the monkeys and seeing 5 out of 7 actual people with Ebola who survived after taking this drug. Salif.
So for why? Because it's like we assume it's like a random variable, like so that we do not use the binomial distribution. Right?
Yeah.
It's like we just assume that.
Yes, it's the endogenous but known thing. So we're trying to explain how many people get cured, but we have a little bit of data on it.
It's like the thing that I'm always thinking about for distribution. But here, because it's success or failure, we have like several independent tries, so to say. We just assume that it is reasonable because it's a random variable. Take the binomial distribution, and additionally, because the success probability that we use is 5/7 because that's
right. So you can think of it, you have 7 Bernoulli random variables, 7 people with Ebola, sum up the number of survivors, that's 5. And so binomial is appropriate if those people are independent of each other. So they didn't infect each other with Ebola or anything like that. So it's kind of plausible that they're independent of each other.
we don't know the
All right. Yes.
Just a quick question.
Nathan, number 1.
The vector that gets put out, what is in that vector?
Realizations of pi that implied your realization of y matched the actual data. So some get kept, some get thrown away. So you're basically grabbing kind of the rightmost part of it and then filling up your out. That's why this CDF for the posterior CDF shifts basically to the right and gets more steep. Andres.
The file Ebola.stan, that file write it in a text editor?
Yeah. It's on Canvas. Yeah, just you can do it in RStudio.
If I was to do it, could I just do it inside RStudio?
And then save it with a file name and then call it with whatever that file name is in the same directory, in the working directory. Yeah. So it's just like reading a file. Back up.
Can you go back 1 slide?
So what we're doing here is in some ways related to that third homework problem where we sampled n from another distribution. Here we're just sampling pi from another distribution essentially.
Yeah, so what makes this a little bit different is we have a condition as to whether to keep our draw or to throw it back. So we want to get 10,000 good ones that we keep. And we're deciding whether to keep it, whether it matches our actual observed data. So this first part of it is just drawing from the prior predictive distribution. And then in order to update our beliefs, we have to select which of those draws we want to keep according to the data. That's one way to update your beliefs, and you can see the CDFs there. Another way to do it would be to make yourself a function that constitutes the numerator of Bayes' rule. And so we have the beta PDF evaluated at pi with shape A and B multiplied by a binomial likelihood with y successes out of n tries, probability pi. Then the denominator of Bayes' rule is just going to be the integral of that function from 0 to 1 with extra stuff a, b, and y. R has an integrate function to do numerical integration. So get the value of that, which is just going to be some number. And then you can plot your posterior PDF, before was the CDF, just evaluate that kernel function, divide by whatever the denominator is. That's the black line there. You could compare it to your prior PDF, which is just the beta distribution with parameters A and B. That's the red line there. And so here we have the same information, but represented in terms of the posterior and prior PDF rather than the CDF. But again, you get the sense that we have more concentrated, more precise beliefs about the success cure probability of this drug after having seen 5 out of 7 people get cured than what our prior beliefs were, which were just based on the monkeys. Sebastian.
So one thing I'm struggling with is that, so thinking about Bayes' rule, there's a certain probability that 5 people would survive Ebola in the first place.
Yes.
So let's say that there was if the normal Ebola survival rate was 5 out of 7, then the fact that 5 out of 7 people survive doesn't actually give us any. I would imply where does sort of the probability of the evidence show up?
Yeah. So Tori informed us that without the drug, you basically have a 0.5 probability of surviving. And this is, telling you that, well, there's about a 0.1 posterior probability that your survival rate is 0.5 or less, having seen the evidence now. So yes, possible that the drug is not effective, but our beliefs are such that it's more optimistic. So we can do it with the PDF numerically. We can do it with the CDF. This was actually the problem that Thomas Bayes solves, not with Ebola, but with a beta prior and a binomial likelihood. Of course, Thomas Bayes did not have $2,500 MacBook to do these calculations on. He had to figure it out with like a feather and ink, stuff like that. And that required him to know that the PDF of the beta distribution can be written like this. And so anytime I put the proportional symbol, I mean these are the terms that involve the random variable pi that we're interested in. And that's known as the kernel of a distribution. The so-called normalizing constant, here represented by large beta, is the reciprocal of the integral of the kernel. So if we take the kernel function, define that in R, just x raised to the power a minus 1, 1 minus x raised to the power b minus 1. We integrate that from 0 to 1, take the value, comes out to be 0.0119 in this situation, which isn't super important. R already has a function that will do that particular integral for you. It's called the beta function, and you get out exactly the same number. And you can write the beta function in terms of the gamma function that we were talking about last time, 3 ways to get whatever the integral of the kernel is. We'll call that capital beta. So whatever that integral is, 0.0119, if we then divide by 0.0119, then the total area under our prior PDF is going to be 1, making it a valid probability density function. And so when we do these problems, the first thing we do is just sort of boil it down to the kernel, and then we'll figure out the integral that we have to put in the denominator later. And in this case, this process works as follows to derive the posterior distribution analytically along the lines of what the Krushke chapter did in the reading. So their survivals are a random variable we're going to assume has a binomial distribution with success probability pi, and there's n people who are exposed to the disease. And so before you see the results, you have this binomial probability mass function, n choose y, y raised to the power number of survivals times 1 minus pi raised to the power number of deaths. And when you observe that 5 out of 7 people with Ebola were cured, then you can use that to update your beliefs about the cure probability. This same function here becomes what's known as the likelihood function. And this is sort of a subtle point relating to the sort of mathematician's definition of a function versus like someone who just programs in R. Remember, the sort of technical mathematical definition of a function is, you know, this rule that gives you a unique mapping from an input set to an output set. So when we see it here, it's a function of y. There can be different values of y. But when you get data, 5 out of 7 people were cured, you're not going to be evaluating it at like y equal 2, y equal 3, etc. So it's not a function of y anymore. It's a function of pi. We're going to evaluate this at all kinds of different values of pi in order to come up with the posterior distribution for the cure probability. And so it's the same mathematical expression. Here it's a function of y. If we call it a likelihood function, then it's a function of the parameters, and we're going to evaluate it only at the value of y that we actually observe in the data. Same thing for n. Anyway, we got the numerator here. We got the denominator, which is the integral of the numerator. Just take the top numerator, call that the kernel. We have from our beta PDF, pi raised to the power a minus 1 times 1 minus pi raised to the power b minus 1. So we got that over there. Then we got the contribution of the likelihood, pi to the y, 1 minus pi to the n minus y. We collect terms, so we now have pi raised to the power a plus y minus 1 times the quantity 1 minus pi raised to the power b plus n minus y minus 1. And if we let a star be a plus 1, and we let b star be b plus n minus y, we now have this expression here, which is the same as the kernel of the beta distribution, just replacing a with a star and b with b star. Thus, we automatically know the posterior PDF, y given a star and b star, it has the kernel of a beta distribution. We know the normalizing constant is going to be 1 over the beta function evaluated at a star and b star. That's going to make it integrate to 1. And so we've concluded, or Thomas Bayes concluded, the posterior distribution in this case is a beta distribution. The prior distribution in this case was a beta distribution. But now with the posterior, having seen the data, it's an updated beta distribution with parameters A star and B star rather than A and B, which are the parameters we put in the prior to start with. So in this particular case, which is relatively simple, seeing the data, it didn't change the family of the distribution. It was beta before, it's beta after. But it's a new beta distribution that has updated shape parameters to it once we see the data. Christine. Just to make it have the same form as the kernel of a beta PDF. So I know what this integrates to. It's the beta function when it's something minus 1 and something minus 1 in the exponents. So I just make a substitution here in order to put it in that form. And then I know in order to normalize it, I just need to divide by the beta function evaluated at A star and B star. And these are my expressions for those. It means it's just a notational way of distinguishing this, which is a function of y, from this, which is a function of pi. So the likelihood function is not a conditional PDF for y given n and y. That's the posterior distribution. So this likelihood function, it's a function, but it doesn't integrate to 1. So it's not a PDF. So we don't use the, this given that notation for something that's not a PDF. Right. So this is our posterior beliefs about the success probability pi, given that we observed n equals 7 people and y equal 5 of them survived after taking the drug. So we, if it was 5 survived but 30 were exposed, that would lead us to a different conclusion. So we're conditioning on n equals 7 here for the posterior distribution. Okay. We can check by putting the green line on these, and it's exactly lined up with the black line that we had before for the CDF and for the PDF. Moreover, we can calculate our posterior mean analytically for a beta distribution and also approximate it by the mean of the draws that we got when we evaluated our stand function. And those are very similar. So basically, whether you do it analytically, whether you do it with numerical integration, or whether you do it with sampling from the prior predictive distribution and then seeing which of the draws of y tilde match your data, you're getting the same answer here, basically equivalent information. So a few key points here. One is that this idea of drawing from the prior predictive distribution and then seeing when it satisfies a constraint underscores a key property of Bayesian analysis, that the posterior PDF is the function that is closest to the prior PDF, but that satisfies a constraint given by the observed data, namely that 5 people were cured out of 7 people who were exposed and took the drug. So you can see it as an optimization problem, but an optimization problem for functions rather than for points. Moreover, at least in one dimension, we have this relationship that the posterior mean is between the prior mean and the sample mean. So reflecting information both from the monkeys and from the results on 5 out of 7 people. If you just look at this expression here and say, well, what if we had a lot more people who took the drug, so n goes to infinity, then the posterior mean is going to converge to y over n, which is the same as the sample mean. So if you get a ton of information from the data, information supplied by your prior is diminished. And the last thing here, you can use your posterior probability mass, posterior PDF, that's wrong, it should say PDF, as your prior PDF for the next data set. So wouldn't it matter if your 7 observations arrived one at a time and you updated your posterior belief 7 times, or they all came at once and you updated it once. It doesn't matter how you get there because you have a coherent belief updating rule. And so after n tries and y successes, your posterior distribution is going to be the same, this beta with A star and B star. And that contains all the information that there is from the past history that you have observed. So this is a very coherent learning rule. Also implies a coherent way to do predictions. So what if you were to observe another 100 cases of people with Ebola and you could give them this drug? How many do you believe would be cured? Well, we could do that with simulations by drawing a realization of pi from the posterior, in this case, beta distribution with shape parameters A star and B star. So we have information. We don't need to draw from the prior of beta anymore. We can draw from the posterior. Then draw realizations of y tilde with a binomial distribution that says size 100 and our realization of pi that we just got. Store those, repeat that over and over again. That's sort of conceptually what it is. In R, you could just vectorize the whole thing. Give me, 10,000 draws from a binomial distribution, each with size 100, but a different realization for the posterior draw of pi. And you get, in this case, something with mean 66.7 out of 100 people cured, but a large variance. And we might ask ourselves then, well, why is the variance in this process when we do the predictions so big? Marlon.
Because it was an N of 7, so it should be that big. And so
Right. You still have a considerable amount of uncertainty as to what the cure probability is. And your uncertainty about pi propagates to your uncertainty as how many out of 100 people would be cured if we were to do this. You can actually work that out analytically. So capital Y is this realization of future Y from binomial distribution, and you want to know what that is, conditional on A star and B star. And that involves the integral of the binomial probability mass function given pi multiplied by your conditional probability distribution for pi given the data. That sort of forms this bivariate distribution that you can integrate pi out of. Again, it's going to involve beta functions, in this case, ratio of the beta functions. In any way, this defines the probability mass function of what's known as a beta binomial distribution. And then if you work out its variance analytically by summing it up from 0 to 100, you get essentially the same number that we were getting before when we did our simulation distributions. So last couple minutes to get to a question that I think Sebastian was implicitly asking: how can we compare this with the frequentist approach? And so the frequentist approach tells us before we see the data, the central limit theorem is going to assure us that the sampling distribution of the sample mean, or the sample proportion in this case, when we have size n data, is going to be asymptotically normal with expectation true pi and variance coming from the binomial distribution pi times 1 minus pi divided by n when we take the sample proportion. So under a null hypothesis that the survival probability is 0.5, which is the same on average as the survival probability from Ebola if you're not given this drug from MAP Biopharmaceutical, there's going to be a 0.9 probability that the sample mean or the sample proportion falls in the interval defined by 0.5, which are a hypothesized value, plus or minus 1.645 if we want a 90% coverage, multiplied by the standard error, which in this case involves 7 observations that we're dividing by. We get this interval 0.19 to 0.81. And that doesn't make exactly as much sense with finite in when discrete data, because that's going to be lumpy. But anyway, you can correct for all that and do in R what's known as exact binomial test. I'm not showing you the code for that because I don't want you to actually do it. But the bottom line here is we get a p-value of 0.2266 for the null hypothesis that the drug is ineffective, with alternative hypothesis that the pure probability is greater than 0.5. And so we would fail to reject the null hypothesis that this drug is ineffective given the data that we have. However, if we go back to those draws that we obtained from the posterior distribution using our Stan function, we can calculate the proportion of times the success probability realization is greater than 0.5, and that's a number 0.9. So we would say the posterior probability that the drug is effective is greater than 0.9. And yet we would, if we were taking a frequentist approach, fail to reject the null hypothesis that the drug results in the same survival rate as without the drug, 0.5, with a 0.1 type 1 error rate. So Bayesian view, there's a greater than 0.9 probability that the drug is effective. Frequentist view, fail to reject the null hypothesis that the drug is ineffective with type 0.1 type 1 error rate. And so how can we reconcile those two conclusions? That's something we'll have to talk about for the rest of the semester, because we're out of time today. Ask questions on Piazza, do the reading, pick it up Tuesday, and I'll post a corrected version of the answer key for the homework that doesn't have the duplicative stuff on it.